Okay, last time we started talking a little bit about stationary points or turning points, which is when the gradient is equal to 0. Okay, so we've got some other questions on these. So find the least value. Find the least value. In other words, find the lowest value given from this here. You might remember that we looked at how to do this by completing the square. And if we completed the square, we could say that it doesn't go any lower than 5. Okay, and when does this occur? Well, it occurs when the bit in the brackets is 0, and that happens when x equals 2. When x equals 2, this becomes 0 and it's 5. So the minimum point, in other words, is 2, 5. Okay, the minimum value 5. We could now, though, also do this with differentiation. X squared minus 4x plus 9 looks something like this. We know that at a minimum, the gradient is equal to 0. So we could actually differentiate it, set it equal to 0, and get the x from here. If we have the x and we want the y, well, we just put the x in and calculate the y. So we put the 2 in and get the 5. So we now have another way of answering this question. Finding turning point of this one here, well, you would struggle to complete the square here, because what do we have? We have an x term and then we have an x to the power of a half. So although here both methods worked, and we've seen method 2 quite a lot in different areas, sometimes when you get given something a bit more complex, you'll need to use differentiation. So I don't really know what this will look like, but I do know that when you differentiate it, so that's x to the half. I wouldn't do this in my head normally, so let's do x to the half. So if I differentiate, I'll get half x to the minus a half, and then minus 1. And I know that if I set that equal to 0, I will be able to find an x value that will tell me the turning point. So if we jump to that line there, move the 1 to the other side, multiply by 2 both sides. Okay, it's quite a bit of manipulation. You might not do it the same way as is done here. Should be able to get to x equals a quarter. When you want to find your y value, you just put your x back in and you will get that value there. So the turning point here is a quarter, a quarter. So differentiation would be necessary for this one because completing the square wouldn't be possible. Finally, there is a third type of stationary point. And you've actually seen this before when you've dealt with cubics, because cubics have a point of inflection there, but they can occur on other functions as well. A maximum, remember, a maximum went from a positive to a negative. A minimum went from a negative to a positive. But this one is quite unique because it goes from a positive to a positive. It just has a point where it goes flat for a moment in between. And it's called a point of inflection. Sometimes POI is put down as. So we could do the same ideas as well. And sometimes perhaps we might find a point of inflection. Point of inflection is just worth saying is a little bit more complicated. You'll see it in year 2. Sometimes a stationary point can be a point of inflection, like this one here, but it's not always the other way around. So how do we know what type of point we've got? Well, there's many different ways of doing it, but here's one way. We know that for all of these, the gradient at that interesting point is 0. That's the common link that we talked about. What we could do then is we could plug in some values of x. So pretend this is minus 5. You might try minus 5.1. And you should get a negative answer from before. You should get a negative gradient. Afterwards, if you put in maybe minus 4.9, you should get a positive. And it lets you piece together what's happening. Here, let's pretend this is minus 1. So minus 1.1. Minus 1.1, you'd expect a positive, and at minus 0.9 a positive again. And that would tell you that you had a point of inflection. And so on. You get the idea. So you can do this by inspection. You can do this by literally substituting in values very, very close to your x here on the left and the right hand side. Make sure the gaps are not too big though. If you go too far away, you might jump over here somewhere, for example. So method 1, look at the gradient just before and just after a point. Find the stationary point with this equation. Stationary point is a signal that we're talking about the gradient function. So dy dx is 4x cubed minus 32. It's a stationary point, so I set it equal to 0. Okay, what can I do? Add 32 to both sides. Divide by 4 gives me 8 equals x cubed. So 2 equals x. Determine whether it is a local maximum or a local minimum or a point of inflection. Okay, well, I found out that it was 2, and the y value should be minus 48, because it did say find the stationary point. So we should probably go for the coordinate here. So the strategy we said is, let's try slightly to the left and slightly to the right. So we know x equals 2. Let's try 1.9, 2, and 2.1. Okay. If we plug in 1.9, if we plug 1.9 in to the gradient function, okay, we will get a negative. In other words, slightly before 2 at 1.9, there is a line that's going down. If we plug in 2.1, so slightly afterwards, we will get, so again, into the gradient function, we will get a value that is positive. So in other words, you have a minimum shape is what you're making there. Now, there are other ways to do this. You could actually plug 1.9 and 2.1 into the equation itself and look what happens to the y values. But this is probably the easiest way to do it. So find out the point and inspect to the left and to the right, but make the gap between them very small. However, there is a more sort of robust method, because sometimes you could accidentally go too far if they're very close to each other. So take a look at this one here. So this is a maximum that I've got, and we know that at the top the gradient is 0. Before we have a positive, and afterwards we have a negative. Nothing new there. We've talked about that already. Now, what we could do is we could use the second derivative. The second derivative is different to the first derivative. This is the first derivative. It's used to find how the y values sort of change, isn't it? It gives you the gradient. In other words, it talks about how the y values change. You know, are they going up or are they going down? The second derivative is given this notation usually. So this is the second derivative. And this talks about how the gradient changes. Now notice I've used the word how. Okay, I haven't said what the gradient is. I've just said how the gradient changes. So for example, the gradient here, let's give it a number. This might be 3. The gradient is going from 3 to maybe let's say 1 to 0 to -1. Let's make it -3. So my question for you there is, how is the gradient changing? Is it getting steeper? Or is it getting, well, mine's gone a little bit blank here, or is it getting, let's say, shallower? No, what should we say? No, let's say, is it getting, let's do it this way. Is it getting more positive? or more negative? I'm not saying what the gradient is. Remember, I'm saying how is the gradient changing? Well, the gradient is actually getting more negative, isn't it? It's going from 3, 1, 0, -1, -3. So how is the gradient changing? That's the bit there on the left-hand side. Well, it's negative. Yeah, it's less than 0. It's negative. So this is the rationale that links the second derivative and things like maxima and minima. If you have a maximum, it means that your gradient is getting less positive, more negative, kind of are being used as the same thing here. Okay, so how it's changing is it's changing in a negative way. So the maximum, this thing here, is going to be negative. For a minimum, it's going to be the other way around. The second derivative is going to be positive. This will seem kind of counterintuitive to you here, and you might have to sort of force yourself to remember this a little bit. But it's really, really good because it means we can just differentiate once and then again. So we can differentiate twice, plug in our x values, and we can tell quite easily if we have a maximum or a minimum. Let's do an example. So we're going to get the second derivative from this one here. 3x5 plus, let's rewrite that, 4x to the -2. We're finding the second derivative. So the first derivative, if we differentiate that, you will get 15x to the 4. And what's that going to be? That's going to be -8x to the -3. The second derivative means you need to take this and you need to differentiate again. Well, that would be 60x to the 3. And double negative there, so plus 24x to the -4. That's what we would have to do. Okay, here the question doesn't have much more, but sometimes we might have to substitute a value into x and find out what happens. Remember, if we got a negative, then we would say it's a maximum. Okay, and sort of so on. Pause the video, have a quick go at that one now on the right hand side to find the second derivative. Okay, I'm going to assume that you've had a go. Don't forget to be careful with that term there. That's the same as a half multiplied by 1 over root x. So you need to be careful with this one. Okay, so just differentiating twice, slightly different notation here, okay? Let's use the second derivative now. So let's do something a little bit more advanced with this. And I think we actually used part of this question earlier. So let's differentiate to start with. So use the second derivative to classify this point. So x to the power 4 minus 32x, yeah. dy dx is 4x cubed minus 32. Now, the stationary point, we actually have been given that already. If we didn't know it, what we would need to do here is we would need to set this one equal to 0, but we did that in one of the earlier slides. I'm not going to do that again. So we know that we're talking about when x equals 2. We know that already, okay? Second derivative, though, we haven't done that. So differentiate again. What do you get? 12x squared only, okay? Now, when we put 2 into 12x squared, what do we get? Well, I'm going to get 2 squared is 4. 12 times 4, I'm going to get 48, okay? 48 is clearly greater than 0. And what's the meaning when the second derivative is greater than 0? Well, it's condition number 1 here at the top. This is a minimum. So therefore, it's a minimum point. And what we're interested in here is showing that you understand that it is a minimum point. But if you actually understand it and your differentiation is good, hopefully you can see there's not an awful lot that you have to do in that question. Okay? And generally, we're sort of moving away now from sketching the idea that it's a minimum and a maximum, and we're going for more of an algebraic approach here. So another go for you there. A full question to have a go at on the board. So pause and have a go. Again, I'm going to assume that you've done that. So we differentiate first. Find the coordinates of the turning points. Remember, the turning points mean you need to set dy dx equal to 0. It also says turning points, which suggests that there's more than one. So 2 minus 10 is one of them, and minus a third, 2.7. Okay, I'm not sure if that's an exact answer. Okay, minus a third, 2.7. So there's 2 turning points. Okay, let's go like that. Differentiate again. Well, that just means differentiate this one again. So 12x minus 10 by the look of it. Hence or otherwise, determine the nature of the turning points. So when you have this one here, you need to just plug in 2 and plug in minus a third, and remember to interpret them correctly. So if we plug 2 in, we will get 12 times 2 is 24, minus 10 is 14. So this one here is positive, so it's a minimum. Okay, minus a third times 12 is going to be minus 4. Okay, minus 10, this is going to be a maximum by the look of it. Okay, and that's the idea. So this is the most efficient way, really, to find out if you have a minimum or a maximum. Time to have a go at some related questions.